Beyond the familiar worlds of our solar system, past the grand storms of Jupiter and the shimmering rings of Saturn, past the tilted blue sphere of Neptune, there exists a realm rarely seen but profoundly important. This is the Kuiper Belt, a vast ring of frozen worlds circling our sun in the twilight zone, where sunlight grows faint and temperatures plunge to nearly absolute zero. Imagine yourself now, drifting peacefully through this remote frontier, where the sun appears merely as the brightest star in a sky filled with countless others. Here, 40 astronomical units from Earth, 40 times the distance between our planet and the sun. The solar wind weakens to a whisper, and the grip of our star's gravity loosens just enough to allow these ancient ice worlds to maintain their slow, eternal dance. The Kuiper Belt extends from approximately 30 astronomical units to 50 astronomical units from the Sun, forming a disc-shaped region that contains remnants from the solar system's formation some 4.6 billion years ago. Named after Dutch-American astronomer Gerard Kuiper, who predicted its existence in 1951. This region remained theoretical until 1992, when astronomers David Jewitt and Jane Liu discovered the first Kuiper Belt object beyond Pluto using the University of Hawaii's telescope on Mauna Kea. As you float through this realm, you notice the profound silence. Space carries no sound, and here, far from the bustle of the inner solar system, that silence feels even more complete. The darkness is not absolute, however. The sun still provides illumination, though at this distance its light takes over 5.5 hours to arrive, traveling at the speed of light across the vast emptiness. That sunlight, though weak, catches on surfaces of ice, water ice, methane ice, ammonia ice, creating subtle glints across the frozen landscape of countless small worlds. The temperature here hovers around negative 220 degrees Celsius, cold enough to freeze nitrogen solid, cold enough that any atmosphere would simply fall as snow to coat the surface. In this environment, ices that would vaporize instantly in Earth's warmth remain stable for billions of years, preserving chemical signatures from the very dawn of our solar system. Scientists estimate the Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers in diameter and countless smaller bodies. The total mass of the belt, however, is surprisingly modest, perhaps just 1/10 the mass of Earth, or even less. This sparse population suggests that the belt once contained much more material, but gravitational interactions with the giant planets, particularly Neptune, scattered most of it away into the inner solar system or out into interstellar space. Your journey through this region reveals objects of remarkable diversity. Some are dark as coal, their surfaces rich in organic compounds created by eons of radiation exposure. Others shine with the pure white of fresh ice. Some tumble rapidly through space, their days lasting mere hours, while others rotate so slowly that their days span Earth weeks. Many travel in pairs or groups, bound together by mutual gravity, dancing around one another in orbital ballets that have continued unchanged since before Earth formed its first oceans. The orbits themselves tell stories. Most Kuiper Belt objects follow relatively circular paths close to the ecliptic plane, that imaginary flat disk where most planets orbit. These are the classical Kuiper Belt objects, residing in the belt's main region between 42 and 48 astronomical units. They maintain stable orbits that Neptune's gravity has barely disturbed over billions of years. Their orbital stability makes them time capsules, preserving conditions and materials from the solar system's youth with minimal alteration. Other objects follow paths more eccentric and inclined, suggesting more dynamic histories involving gravitational encounters with Neptune. Some objects, called resonant Kuiper Belt objects, maintain orbits synchronized with Neptune's. For every 3 times Neptune orbits the Sun, these objects orbit exactly twice, a stable gravitational relationship that prevents close approaches between them and the giant planet. Pluto itself, the most famous Kuiper Belt object, follows this 2 to 3 resonance pattern, as do numerous smaller bodies called plutinos in recognition of this shared orbital characteristic. As you drift deeper into the belt, you pass objects both familiar and strange. These are not planets in the classical sense, yet they are worlds nonetheless, each with its own surface features, its own composition, its own unique story written in ice and rock across billions of years. Some have moons, tiny companions locked in gravitational embrace. Others show evidence of ancient impacts, their surfaces scarred by collisions with fellow inhabitants of this crowded region. The belt's existence helps explain phenomena observed in our night sky. Short-period comets, those that return to the inner solar system on timescales of decades to centuries, originate primarily from the Kuiper Belt. Gravitational perturbations occasionally nudge objects out of the belt, sending them on long, elliptical plunges toward the sun. As these icy bodies approach the inner solar system's warmth, their frozen surfaces begin to sublimate, creating the glowing comas and spectacular tails that have inspired humanity for millennia. Scientists study the Kuiper Belt not merely out of curiosity about distant, frozen worlds, but because it offers invaluable insights into planetary formation and the early solar system. The belt's objects are thought to be planetesimals, building blocks that never quite assembled into a planet due to the region's low density and Neptune's disruptive gravity. By examining their composition, scientists can determine what materials were present in our solar system's outer regions during the epoch of planet formation, materials that partly compose the cores of the giant planets themselves. Here in this frozen frontier, you feel the profound age of these objects. They have orbited the sun for almost the entire lifetime of our solar system, witnesses to all that has transpired in the warmer regions closer to the sun. The formation of planets, the bombardment that scarred the inner planets and moon, the emergence of life on Earth, the rise and fall of countless species, the eventual appearance of humans gazing outward, trying to understand their cosmic context. The Kuiper Belt represents the solar system's attic, a storage region for materials and memories from ages past. As you float peacefully through this domain, you become part of that ancient story, a consciousness drifting through time and space, surrounded by the building blocks of worlds, bathed in the faint light of our distant sun, embraced by the cosmic silence that allows for deep reflection and profound rest. Among all the inhabitants of the Kuiper Belt, one stands out in human consciousness: Pluto. Discovered in 1930 by Clyde Tombaugh at Lowell Observatory in Flagstaff, Arizona, Pluto captured imaginations for 76 years as our solar system's ninth planet. Its reclassification in 2006 as a dwarf planet sparked passionate debate, but scientific understanding, not sentiment, drove this decision. A recognition that Pluto is merely the first discovered and perhaps most famous member of a vast population of similar worlds. As you approach Pluto in your peaceful drift through the Kuiper Belt, the dwarf planet gradually resolves from a point of light into a world of surprising complexity. At approximately 2,370 kilometers in diameter, about two-thirds the diameter of Earth's moon, Pluto is substantial enough to have pulled itself into a roughly spherical shape through its own gravity, meeting one of the criteria for dwarf planet status. Its surface, a patchwork of terrains ranging from smooth plains to rugged, cratered highlands, tells of a geologically complex history that scientists are still working to understand. Pluto orbits the Sun at an average distance of 39.5 astronomical units, though its elliptical orbit brings it as close as 29.7 astronomical units and as far as 49.3 astronomical units. This orbital eccentricity means Pluto sometimes crosses inside Neptune's orbit, though the 2 to 3 resonance ensures they never collide. One Pluto year, one complete orbit around the Sun takes approximately 248 Earth years. Imagine, when Pluto completes a full orbit, more than 2 human lifetimes have passed on Earth. The dwarf planet rotates on its axis once every 6.4 Earth days, but in a direction opposite to most planets, retrograde rotation, like Venus and Uranus. This slow, backward spin, combined with the orbital period of its largest moon Charon, creates a unique situation. Pluto and Charon are tidally locked to each other, always presenting the same face to one another as they orbit their common center of mass. They form a binary system, dancing through space as partners rather than as planet and satellite. Charon, discovered in 1978 by astronomer James Christie, measures approximately 1,200 kilometers in diameter, roughly half Pluto's size. This unusually large moon-to-planet ratio makes the Pluto-Charon system unique in our solar system. The two worlds orbit their common center of gravity, called the barycenter, which lies in the space between them rather than inside Pluto's body. Every 6.4 days, they complete one mutual orbit, their gravitational embrace holding them in perfect synchronization. Beyond Charon, Pluto has 4 smaller moons, all discovered between 2005 and 2012 using the Hubble Space Telescope. Nix and Hydra, discovered in 2005, are followed by even tinier Kerberos and Styx. These small moons orbit in the same plane as Charon, likely formed from debris created when a massive impact in Pluto's past blasted material into orbit, the same event that may have created Charon itself. The New Horizons spacecraft, launched by NASA in 2006, conducted a historic flyby of Pluto on July 14, 2015, providing humanity's first close-up views of this distant world. The images and data transmitted back to Earth revolutionized scientific understanding of Kuiper Belt objects, revealing Pluto as far more geologically active and diverse than anyone had anticipated for such a cold, distant world. New Horizons revealed a surface painted in subtle shades of red, brown, tan, and white, colors produced by complex organic molecules called tholins formed when methane ice is exposed to solar radiation and cosmic rays. The heart-shaped feature, informally named Tombaugh Regio, dominates one hemisphere. This region's western lobe, Sputnik Planitia, is a vast plain of nitrogen ice showing no impact craters, indicating recent resurfacing, perhaps within the last 10 million years, a geological blink of an ice suggesting active processes continuing today. Scientists studying Sputnik Planitia have observed polygon-shaped cellular patterns in the ice, each cell approximately 30 kilometers across. These patterns suggest convection in the nitrogen ice layer, warmer ice slowly rising from below, spreading across the surface, cooling, and then sinking again in the cell boundaries. This process, powered by heat from Pluto's interior and the phase changes in nitrogen ice, constantly renews the surface, erasing impact craters and maintaining the plane's youthful appearance. Mountains of water ice, some reaching 3 to 4 kilometers high, rise near Sputnik Planitia's borders. On Pluto, water ice is the bedrock, strong as granite at these frigid temperatures. These mountains appear to float on the denser nitrogen ice plains, like icebergs on Earth's Arctic Ocean. The forces that raised these peaks remain under investigation, but they demonstrate that geological processes, tectonics, perhaps driven by tidal interactions with Charon or by internal heat, remain active in this ancient world. Elsewhere on Pluto's surface, New Horizons photographed a region nicknamed Tartarus Dorsa, covered in bizarre, blade-like ridges of methane ice, each blade standing hundreds of meters tall and aligned roughly north-south. These formations, unique in the solar system, likely formed through sublimation erosion, where methane ice sublimates directly from solid to gas, leaving behind resistant ridges. The process requires countless cycles of freezing and sublimation over millions of years, sculpting the landscape into these extraordinary formations. Pluto possesses a thin atmosphere, primarily nitrogen with traces of methane and carbon monoxide, which extends surprisingly far into space, up to 1,600 kilometers above the surface. This atmosphere freezes and falls as snow when Pluto reaches the most distant points in its orbit, and the temperature drops even further, then sublimes back into gas as Pluto approaches perihelion. New Horizons detected blue haze layers in this atmosphere, created by the same complex organic molecules that color the surface, and measured atmospheric escape rates, suggesting Pluto loses approximately 500 tons of nitrogen to space every hour. The dwarf planet's density, about 1.9 times that of water, indicates a composition of approximately 70% rock and 30% ice, similar to other Kuiper Belt objects and to Neptune's moon Triton, which scientists believe is a captured Kuiper Belt object. This composition tells us about the building blocks available in the outer solar system during planet formation, and suggests that if Pluto had formed closer to the Sun or in a denser region of the protoplanetary disk, it might have accumulated enough additional mass to become a fully fledged planet. The reclassification of Pluto in 2006 came after astronomers discovered numerous objects in the Kuiper Belt of comparable or even greater size. Eris, discovered in 2005, is slightly more massive than Pluto, forcing the International Astronomical Union to define what constitutes a planet. The new definition requires that a planet must orbit the Sun, be massive enough to achieve hydrostatic equilibrium, a nearly spherical shape, and have cleared its orbital neighborhood of other objects. Pluto meets the first two criteria, but not the third. The Kuiper Belt contains thousands of objects crossing through Pluto's orbital space. Thus, Pluto became the prototype of a new category: dwarf planets, objects large enough to be spherical but not gravitationally dominant in their orbital zones. This classification, rather than diminishing Pluto, actually elevated its importance as the doorway through which humanity began to understand the vast population of the Kuiper Belt. Pluto is not lonely in exile, but rather a prominent member of a diverse community of frozen worlds. As you continue your peaceful drift past Pluto and Charon, these worlds slowly recede behind you, twin spheres locked in their eternal dance. You leave them spinning together in the darkness, their surfaces illuminated by the faint, cold light of the distant sun, their geological processes continuing their slow work, their story continuing to unfold across the millennia, whether witnessed by human eyes or not. They are ancient and they are patient, and they will continue their journey long after humanity has gone, silent sentinels at the edge of sunlight. Drifting onward from Pluto, you enter the heart of the classical Kuiper Belt, the region between 42 and 48 astronomical units where objects orbit the Sun in relatively circular, low-inclination paths. These are the cold, classical objects, not cold in temperature, as all Kuiper Belt objects exist at similar frigid temperatures, but cold in their orbital dynamics, meaning they have experienced minimal gravitational perturbation since the solar system's formation. The classical belt represents the most pristine sample of the protoplanetary disk's outer regions. While planets formed, migrated, and gravitationally reshaped much of the solar system, these objects remained relatively undisturbed, slowly orbiting in the same paths they have followed for 4.6 billion years. They are time capsules, preserving information about the composition, temperature, and conditions of the outer solar system during the epoch when planets were being born. The objects here vary tremendously in size. The largest classical Kuiper Belt objects reach dimensions of several hundred kilometers, massive enough to have differentiated interiors, meaning their internal heat, from radioactive decay and residual formation energy, was sufficient to separate heavier rocky materials that sank toward the center from lighter ices that rose toward the surface. Most objects, however, are much smaller, ranging from tens of kilometers down to boulders and pebbles too small to detect with current telescopes. Observations reveal that classical Kuiper Belt objects exhibit a range of colors, from gray to reddish. These colors provide clues about surface composition and history. Grayer objects likely have experienced recent collisions that exposed fresh ice beneath radiation-darkened surfaces, or they may have formed in slightly different regions of the protoplanetary disk where ices of different compositions condensed. Redder objects typically show surfaces rich in organic tholins, complex carbon-based molecules created when simpler ices are irradiated by ultraviolet light and cosmic rays over billions of years. Scientists have discovered that many classical Kuiper Belt objects exist in binary or multiple systems, two or more objects orbiting each other. The frequency of these binary systems in the classical belt exceeds what would be expected from random gravitational capture, suggesting they form together, perhaps fragmenting from a single larger object or forming simultaneously from the same region of the protoplanetary disk. These binary systems provide valuable data about the object's masses and densities, allowing scientists to constrain models of their internal structures and compositions. One notable classical Kuiper Belt object is Makemake, discovered in 2005 by a team led by Michael Brown at Caltech. Makemake measures approximately 1,430 kilometers in diameter, making it the second brightest Kuiper Belt object as seen from Earth after Pluto. Its surface is covered in methane and ethane ices, giving it a bright, reflective appearance. In 2016, observations during a stellar occultation, when Makemake passed in front of a distant star, revealed that Makemake has no substantial atmosphere, suggesting its surface temperature and vapor pressure are not conducive to maintaining gaseous nitrogen or methane around the world. Another significant resident is Haumea, also discovered in 2005, notable for its elongated, football-like shape and rapid rotation. Haumea spins once every 4 hours, the fastest rotation of any known equilibrium body in the solar system larger than 100 kilometers. This rapid spin distorts the dwarf planet into an ellipsoid, with axes measuring approximately 2,300 by 1,700 by 1,000 kilometers. Haumea possesses 2 known moons and a thin ring system, making it one of the few small bodies in the outer solar system known to have rings. The origin of Haumea's unusual properties likely lies in a massive collision early in solar system history. Models suggest that a large impactor struck a progenitor body, shattering it and imparting angular momentum that continues to spin Haumea today. The impact also created a family of smaller objects sharing similar orbital characteristics and reflective properties, all apparently originating from the same parent body. This Haumea collisional family provides a rare opportunity to study the aftermath of a giant impact in the outer solar system, offering insights into collision physics and the internal structures of large Kuiper Belt objects. As you drift peacefully through the classical belt, you pass countless smaller bodies, each a world unto itself, each with its own history of collisions, radiation exposure, and slow chemical evolution. Some objects display surprisingly bright patches, possibly fresh ice exposed by recent impacts or landslides. Others appear uniformly dark, their surfaces aged by billions of years of radiation exposure, their primordial ices transformed into complex organic materials that no longer sublimate in the weak sunlight. The population structure of the classical belt offers clues about solar system formation and evolution. Astronomers have detected a sharp outer edge to the belt at approximately 48 astronomical units, beyond which the population density drops dramatically. This edge likely results from Neptune's gravitational influence during the solar system's youth. Models suggest Neptune formed closer to the Sun than its current position and migrated outward over tens of millions of years, scattering planetesimals as it went. This migration sculpted the Kuiper Belt structure, clearing material from some regions while trapping objects in others. The classical belt also contains objects with surprisingly high inclinations, orbits tilted significantly relative to the ecliptic plane. These hot classical objects, despite the confusing name referring to their dynamic orbits rather than temperature, likely experienced more gravitational interactions with Neptune during the era of planetary migration. Their excited orbits, more inclined and eccentric than their cold classical cousins, record the dynamical violence of the young solar system when giant planets moved and gravitational chaos reigned. Studying the size distribution of classical Kuiper Belt objects helps scientists understand accretion processes in the outer solar system. Observations reveal more large objects than predicted by simple collisional evolution models, suggesting that kilometer-sized planetesimals formed rapidly and directly from the protoplanetary disk, possibly through gravitational instabilities that caused regions of the disk to collapse directly into solid bodies, bypassing gradual accumulation from smaller particles. The classical belt also serves as a source region for centaurs, objects that have been gravitationally scattered inward from the Kuiper Belt and now orbit among the giant planets. Over millions of years, gravitational perturbations nudge classical Kuiper Belt objects into unstable orbits, eventually sending them inward. These centaurs represent the first stage in a journey that may ultimately bring them into the inner solar system as short-period comets, their ices sublimating to create glowing tails visible from Earth. Here in the classical belt, surrounded by ancient worlds in their primordial orbits, you feel the deep time represented by these objects. They are older than Earth's oldest rocks, older than any geological feature on our planet's ever-changing surface. They have witnessed the entire history of our solar system from a distance, unchanging and unchanged, silent witnesses to all that has transpired closer to the sun. In their frozen silence, they offer peace and perspective, a reminder that our human concerns unfold against a cosmic backdrop of timescales and distances almost beyond comprehension. Let this realization wash over you like a wave of calm, allowing your mind to rest in the presence of such ancient, patient worlds. As you drift beyond the classical belt's relative order, you enter regions where orbits become more eccentric, more inclined, more obviously shaped by Neptune's gravitational influence. These are the domains of the scattered disk and resonant populations, objects whose paths through space tell stories of gravitational encounters and dynamic instability that scattered them from their formation regions. The scattered disk extend from approximately 30 astronomical units outward, overlapping with the classical belt, but distinguished by highly elliptical orbits with large perihelia. Closest approaches to the Sun that bring some objects inside Neptune's orbit at times. These objects orbit more chaotically, their paths taking them far above and below the ecliptic plane, their orbital periods spanning centuries or millennia. Scattered disk objects are thought to be former residents of the planetary region who were gravitationally ejected outward by close encounters with Neptune. Unlike classical belt objects that avoided significant perturbation, scattered disk objects experienced Neptune's gravitational influence more directly, receiving enough energy to be flung into the outer solar system on highly elliptical trajectories. This scattering process continues today at a much slower rate, occasionally sending objects deeper into space or, conversely, deflecting them inward toward the realm of the giant planets. The most famous scattered disk object is Eris, discovered in 2005 by Michael Brown, Chad Trujillo, and David Rabinowitz. Eris measures approximately 2,326 kilometers in diameter, making it nearly identical in size to Pluto, but slightly more massive. This discovery prompted the International Astronomical Union to formally define planet, leading to Pluto's reclassification. Eris orbits the Sun at an average distance of 68 astronomical units, but its highly eccentric orbit brings it as close as 38 astronomical units and as far as 98 astronomical units, nearly 100 times Earth's distance from the Sun. Eris's surface is remarkably reflective, with an albedo, the fraction of sunlight it reflects, of approximately 96%, making it one of the most reflective objects in the solar system, comparable to fresh snow on Earth. This high reflectivity suggests a surface coated in methane ice that regularly refreshes itself. When Eris approaches perihelion, increased solar heating causes methane to sublimate, creating a temporary thin atmosphere. As Eris recedes toward aphelion and temperatures drop, this atmospheric methane freezes and falls as snow, coating the surface with fresh, bright ice that covers any darker, radiation-processed material. Eris has one known moon, Dysnomia, discovered in 2005. Observations of Dysnomia's orbit allowed scientists to calculate Eris's mass precisely, revealing it to be approximately 27% more massive than Pluto despite being similar in size. This higher density indicates a proportionally larger rocky component, suggesting Eris formed in a region of the protoplanetary disk where rocky materials were more abundant relative to ices, or that it experienced different collisional and evolutionary processes than Pluto. Another notable scattered disk object is Sedna, discovered in 2003 by Brown, Trujillo, and Rabinowitz. Sedna follows one of the most extreme orbits known, with a perihelion of 76 astronomical units, never approaching anywhere near Neptune, and an aphelion of approximately 936 astronomical units, well into the inner Oort cloud. Sedna's orbital period is approximately 11,400 years, meaning the last time it was at its current position in its orbit, human civilization was just beginning to develop agriculture. Sedna's orbit is so detached from Neptune's influence that its origin remains puzzling. Several theories attempt to explain such extreme orbits. Perhaps a passing star gravitationally perturbed Sedna in the solar system's youth. Perhaps Sedna formed in the Sun's birth cluster and was captured. Perhaps an as-yet undetected planet in the outer solar system shepherds these distant objects into such orbits. The mystery of Sedna and similar objects like 2012 VP 113 represents one of the most intriguing questions in planetary science, potentially pointing to undiscovered structure in the outer solar system. Resonant populations occupy orbits whose periods maintain precise mathematical relationships with Neptune's orbital period. The most prominent resonance is the 2 to 3 resonance occupied by Pluto and the Plutinos. These objects complete exactly 2 orbits for every 3 of Neptune's, a stable configuration that prevents close encounters despite orbital paths that cross Neptune's on paper. This resonance effectively protects Plutinos from Neptune's gravitational disruption, allowing them to survive in what would otherwise be unstable orbits. Other resonances host smaller populations. The 1 to 2 resonance, where objects orbit once for every 2 Neptune orbits, contains the Titinos. The 2 to 5 resonance and others each host their own populations. These resonances act as gravitational safe havens, stable zones where objects can persist despite orbiting in regions where non-resonant objects would be ejected on relatively short timescales. The distribution of objects among different resonances provides constraints on models of Neptune's migration, as the giant planet's outward journey would have swept resonances outward with it, capturing objects along the way. The origin of these resonant populations likely involves Neptune's migration through the early solar system. As Neptune moved outward, pushed by gravitational interactions with smaller planetesimals, its orbital resonances swept outward with it like gravitational nets, capturing objects and carrying them along. This process would have trapped a fraction of the original population into resonant orbits while scattering most objects out of the region entirely, either inward toward the realm of the giant planets or outward toward the scattered disk and beyond. Studying the scattered disk and resonant populations provides crucial evidence about the early solar system's dynamic evolution. The very existence of these populations, their orbital distributions, and their physical properties serve as fossils of gravitational interactions that occurred billions of years ago. By combining observations with sophisticated computer simulations of solar system formation and evolution, scientists can work backward to constrain models of how, and when a giant planet's migrated, how much mass existed in the primordial Kuiper Belt, and what processes shaped the solar system's architecture. As you drift through these regions of eccentric orbits and gravitational resonances, you witness the profound influence that giant planets exert over vast distances and timescales. Neptune, 40 astronomical units away, reaches out with its gravity across billions of kilometers to shape the orbits of objects it will never directly encounter. The dance between planet and planetesimal, played out over millions of years, continues to slowly reshape this region, gradually depleting the scattered disk as objects are either ejected from the solar system entirely or sent on comet-like plunges toward the inner solar system. These scattered and resonant objects, following their complex gravitational choreography, embody the dynamic nature of our solar system. Not a static arrangement, but an ever-evolving system where objects still move, orbits still change, and gravitational interactions continue to play out across deep time. Yet despite this dynamic quality, the changes occur so slowly from a human perspective that the configuration would appear nearly unchanged across thousands of human lifetimes. There is something deeply peaceful in this realization. Vast changes unfolding so gradually that stability emerges from the slow dance of gravity and motion. Rest in this thought as you continue your drift through the frozen frontier. The Kuiper Belt objects carry within their frozen bodies a chemical record of the solar system's formation. By analyzing their composition, the ices, rocks, and organic materials that constitute these worlds, scientists can reconstruct conditions in the protoplanetary disk 4.6 billion years ago and trace the subsequent chemical evolution driven by radiation, impacts, and internal processes. The primary ices found on Kuiper Belt objects include water ice, methane ice, nitrogen ice, carbon monoxide ice, and ammonia ice. The relative abundances of these ices vary from object to object, reflecting differences in formation location, subsequent evolution, and perhaps collisional history. Water ice dominates the composition of most objects, remaining stable across the full range of temperatures found in the Kuiper Belt. At these frigid temperatures, around -220 degrees Celsius, water ice is as hard as granite on Earth, serving as the structural bedrock of these worlds. More volatile ices like methane and nitrogen can sublimate directly from solid to gas, even at Kuiper Belt temperatures, though very slowly. Objects large enough to maintain gravitational fields, like Pluto and Eris, can retain these volatile ices on their surfaces and even maintain tenuous atmospheres during warmer portions of their orbits. Smaller objects, lacking sufficient gravity, gradually lose volatile ices to space over billions of years through sublimation and solar wind sputtering, leaving behind surfaces increasingly enriched in water ice and non-volatile materials. Spectroscopic observations, analyzing the wavelengths of sunlight reflected from Kuiper Belt objects, allow astronomers to identify surface compositions without directly visiting these distant worlds. Different ices absorb and reflect light at characteristic wavelengths, creating spectral fingerprints that can be detected even across billions of kilometers. Observations using large ground-based telescopes equipped with sensitive infrared spectrographs, as well as space telescopes like Hubble and the James Webb Space Telescope, have revealed the diversity of Kuiper Belt compositions. Water ice shows strong absorption features in infrared wavelengths around 1.5 and 2 micrometers. Methane exhibits absorption band around 1.7, 2.2, and 2.3 micrometers. Nitrogen ice, more challenging to detect, shows weaker features around 2.1 micrometers. By carefully analyzing the depths and shapes of these absorption features, scientists can determine not just which ices are present, but also their physical state. Crystalline versus amorphous ice, pure versus mixed with other materials, fresh versus radiation processed. The detection of methane on several large Kuiper Belt objects, including Pluto, Eris, and Makemake suggests these worlds have surface temperatures and pressures near the triple point of methane, where solid, liquid, and gas phases can coexist. This creates possibilities for interesting surface processes, including seasonal cycles of sublimation and deposition, and potentially even methane rain or snow during brief warm periods in their orbits. Though such processes would be far less dramatic than Earth's water cycle. Beyond simple ices, Kuiper Belt objects display evidence of complex organic chemistry. Surfaces often show reddish or brownish coloration attributable to tholins. Complex organic macromolecules formed when simpler molecules like methane, nitrogen, and carbon monoxide are exposed to ultraviolet radiation and cosmic rays. Laboratory experiments simulating Kuiper Belt conditions have successfully produced tholins, revealing them to be complex mixtures of hundreds of different organic compounds, including some of the prebiotic molecules relevant to the chemistry that led to life on Earth. The presence of tholins on Kuiper Belt objects demonstrates that organic chemistry occurs throughout the solar system, not just in the warm, liquid environments of planetary surfaces. The organic inventory delivered to the early Earth via Kuiper Belt comets likely contributed to the raw materials from which life eventually emerged. In this sense, the Kuiper Belt represents not just a distant, frozen frontier, but a chemical laboratory that has been producing organic molecules for billions of years, some fraction of which reached Earth and other inner solar system bodies. Density measurements, obtained by observing binary Kuiper Belt objects and calculating masses from their mutual orbits, provide information about internal composition. Most large Kuiper Belt objects show densities between 1.5 and 2.5 grams per cubic centimeter, consistent with mixtures of rock and ice. These densities suggest that Kuiper Belt objects formed from materials similar to those that went into building the cores of the giant planets. Rocky silicate materials mixed with various ices in roughly similar proportions as found in primitive meteorites called carbonaceous chondrites. Some Kuiper Belt objects may have differentiated interiors, meaning they were once warm enough, from a combination of radioactive decay, especially of short-lived isotopes present in the early solar system, and gravitational energy from impacts, to allow denser rocky material to sink toward the center while lighter ices rose toward the surface. Models suggest that objects larger than a few hundred kilometers in diameter likely experienced at least partial differentiation, creating rocky cores surrounded by ice mantles. Smaller objects probably remain largely undifferentiated, thoroughly mixed conglomerates of rock and ice frozen in place since their formation. The detection of crystalline water ice on some Kuiper Belt objects provides evidence of past heating. Water ice formed in cold environments naturally takes an amorphous structure, disordered at the molecular level. To become crystalline, with water molecules arranged in ordered patterns, ice must be warmed above approximately 130 Kelvin, still well below freezing by Earth standards, but significantly warmer than most Kuiper Belt surface temperatures. The presence of crystalline ice suggests either that objects formed in warmer regions and were later scattered outward, or that internal or impact heating warmed surface materials after formation. Cryovolcanism. Volcanism involving eruption of liquid or vaporized ice rather than molten rock may have occurred on the largest Kuiper Belt objects. Evidence from Pluto, including smooth plains that appear to have flowed across older terrain, suggests possible cryovolcanic processes in its past or even present. Such activity would require internal heat sources, potentially from radioactive decay in rocky cores or from tidal heating due to gravitational interactions with moons. Cryovolcanism could bring subsurface materials to the surface, refreshing surface compositions and creating opportunities for interesting chemistry, where liquid water or water-ammonia mixtures interact with other materials. Ammonia, detected on some Kuiper Belt objects, serves as an effective antifreeze when mixed with water ice, significantly lowering the melting point of the mixture. A water-ammonia ocean could remain liquid at temperatures as low as 176 Kelvin, potentially allowing subsurface oceans to exist inside some of the largest Kuiper Belt objects even today. Such oceans, if they exist, would be protected from the harsh radiation environment of space by overlying ice layers, potentially providing stable environments where complex chemistry could occur over billions of years. The chemistry recorded in Kuiper Belt objects also constrains models of the solar nebula for which the solar system formed. The temperature gradient in the protoplanetary disk controlled which materials could condense at different distances from the forming sun. Close to the sun, only refractory materials like metals and silicates could remain solid. Farther out, water ice could condense beyond the snow line. Even farther out, more volatile ices like carbon monoxide and methane could condense. The compositions of Kuiper Belt objects, recording which ices were present at 40 to 50 astronomical units, help map the temperature and chemical structure of the outer protoplanetary disk. Isotope ratios, the relative abundances of different isotopes of the same element, provide additional chemical clues. For example, the ratio of deuterium to normal hydrogen in water ice can indicate formation temperature, as chemical reactions at different temperatures preferentially incorporate different isotopes. Measurements from comets originating in the Kuiper Belt showed deuterium to hydrogen ratios generally higher than Earth's ocean water, suggesting that Kuiper Belt comets alone did not supply all of Earth's water. Some must have come from warmer sources, perhaps asteroids, complicating models of volatile delivery to the early Earth. As you drift through the Kuiper Belt, these chemical signatures surround you in the ice beneath your consciousness. Each surface you pass contains information, a chemical library written in frozen molecules, a record of ancient processes, a testament to the complexity that emerges even in the coldest, most remote regions of our solar system. The frozen frontier is not chemically dead, but rather preserves a rich inventory of materials and molecules, slowly evolving under the influence of radiation and rare collisions, patiently waiting to reveal its secrets to any who make the journey to study it. Though the Kuiper Belt appears peaceful in its cold stillness, violence occasionally punctuates the long quietude. Collisions between objects, rare from a human timescale, but inevitable over billions of years, have profoundly shaped the population. Impact craters scar surfaces, collisional families share similar orbits, and some objects are likely fragments from catastrophic disruptions of larger parent bodies. The collision rate in the Kuiper Belt is considerably lower than in the asteroid belt between Mars and Jupiter. The Kuiper Belt's vast volume, combined with relatively circular orbits for classical belt objects, means objects rarely approach each other closely enough for impacts. Nevertheless, with billions of years available, even rare events accumulate. Computer simulations suggest that large Kuiper Belt objects experience significant impacts, those capable of creating craters larger than 10 kilometers, perhaps once every 100 million years on average, though considerable uncertainty exists in these estimates. When collisions do occur, the physics differs substantially from impacts on terrestrial planets. Impact velocities in the Kuiper Belt average around 1 to 2 kilometers per second, much slower than typical asteroid belt collisions at 5 kilometers per second, or impacts on the inner planets at 10 to 20 kilometers per second or higher. These relatively gentle collisions mean that Kuiper Belt impacts deliver less energy per unit mass, reducing the degree of heating, melting, and vaporization that occurs. At the frigid temperatures of the Kuiper Belt, impact physics also changes. Ice strength increases dramatically at extreme cold, making water ice as strong as rock. However, volatile ices like nitrogen and methane remain relatively weak even when frozen. This strength dichotomy means impacts in a volatile-rich surfaces may excavate craters with different morphologies than impacts into water ice-dominated targets. The ejecta from impacts, material blasted away from the crater, may include solid chunks, ice vapor, and organic-rich dust, each following different trajectories depending on particle size and velocity. New Horizons imagery of Pluto and its moon Charon revealed heavily cratered terrains in older, presumably less geologically active regions. Crater counts, determining the number of craters of different sizes per unit area, allow scientists to estimate surface ages. More craters indicate older surfaces that have been exposed to impacts for longer periods. Sputnik planitia on Pluto, showing no craters, must be extremely young, perhaps less than 10 million years old, and possibly still active today. Other regions show intermediate crater densities, suggesting diverse geological histories with episodes of resurfacing interspersed with periods of cratering accumulation. Charon's northern hemisphere displays a heavily cratered landscape, with one particularly large impact basin informally named Mordor Macula, though its dark coloration appears to result from radiation processing rather than impact processes. The largest crater, approximately 250 kilometers across, testifies to a violent impact early in Charon's history. The survival of such large craters indicates minimal geological activity has affected this hemisphere for billions of years, contrasting with regions showing evidence of tectonic resurfacing. Some Kuiper Belt objects, particularly smaller ones, may be collisional fragments rather than primordial objects that formed directly from the protoplanetary disk. The size distribution of Kuiper Belt objects shows an excess of bodies around 100 kilometers in diameter compared to what pure collisional evolution would predict, but smaller objects may indeed be collisional shards from the breakup of larger parents. Distinguishing primordial from collisional objects remains challenging without detailed observations of specific bodies. Collisional families, groups of objects sharing similar orbits and compositions, provide direct evidence of catastrophic disruptions in the Kuiper Belt. The most famous example is the Haumea family, where Haumea itself and numerous smaller bodies share orbital characteristics and water ice-rich compositions consistent with formation from a single parent body. The collision that created this family must have been energetic enough to shatter a large object hundreds of kilometers across, imparting angular momentum that left Haumea spinning rapidly while scattering fragments into slightly different orbits that they follow today. Binary systems in the Kuiper Belt may also originate from collisions, though alternative formation mechanisms exist. Some binaries could form through gentle collisions where two objects stuck together rather than shattering, a process called accretion. Others might form through three-body interactions where three objects approach each other, and two end up bound while the third carries away excess energy and angular momentum. Still others could have formed directly as binaries when the protoplanetary disk underwent gravitational instability, collapsing into multiple bound objects simultaneously. Collisions gradually grind down the Kuiper Belt population over time through a process called collisional cascade. Large objects occasionally shatter into numerous smaller fragments. These fragments eventually collide with each other and with other objects, breaking into even smaller pieces. This cascade continues down to dust-sized particles, which are eventually removed from the solar system by radiation pressure from sunlight. The collisional cascade means the Kuiper Belt is slowly eroding, its mass decreasing over billions of years, though the process is sufficiently slow that the belt will remain substantially populated for billions of years to come. Dust produced by Kuiper Belt collisions contributes to the zodiacal light observed from Earth, a faint glow visible after sunset or before sunrise along the ecliptic plane caused by sunlight scattering off interplanetary dust particles. While most zodiacal dust originates from comets and asteroids, the outer solar system contributes to a diffuse dust population extending well beyond Neptune's orbit. This dust slowly spirals inward under the influence of radiation pressure and the Poynting-Robertson effect, eventually either falling into the sun or being ejected from the solar system. The impact history recorded in Kuiper Belt objects also provides information about the evolution of the impactor population over time. The early solar system experienced far higher impact rates during the period of heavy bombardment, roughly 4 billion years ago, when the last remnants of planet formation were being swept up. The late heavy bombardment, a hypothesized spike in impact rates around 3.9 billion years ago, potentially triggered by the giant planet's migration, should have affected the Kuiper Belt as well as the inner solar system. Crater densities on Kuiper Belt objects, if measured in sufficient detail, could provide constraints on the timing and intensity of this bombardment. As you drift through this realm, you pass surfaces ancient and scarred, recording billions of years of occasional violence, punctuating vast stretches of tranquility. Each crater is a timestamp, a marker of a moment when two objects converged in this vast space, their paths intersecting in violent conjunction. Yet even this violence occurs in slow motion from a cosmic perspective. Impacts separated by millions of years, energies dissipating instantly into the cold vacuum, leaving only scars to mark where brief chaos interrupted the eternal peace. The Kuiper Belt absorbs these moments of violence into its deep time, where even cataclysms become merely small ripples in an ocean of serenity. Many Kuiper Belt objects do not travel alone through the cosmic dark. Moons orbit numerous objects, bound by mutual gravity in dances that have continued for billions of years. Some objects even possess ring systems, delicate structures of dust and ice particles orbiting in precise planes. These systems reveal gravitational dynamics playing out across the frozen frontier, where even small masses can capture companions and shape elegant structures. The formation of moons in the Kuiper Belt differs from moon formation around planets. Most planetary moons either formed from circumplanetary disks of material during planet formation, or captured asteroids or comets that wandered too close and were gravitationally trapped. Kuiper Belt moons, however, likely formed primarily through giant impacts, collisions energetic enough to blast material into orbit around the surviving object, where it gradually coalesced into one or more moons. Pluto's moon system exemplifies impact-formed satellites. Charon likely formed from debris created when a large impactor struck Pluto early in solar system history, blasting material into orbit. This debris then coalesced into Charon, which subsequently tidally evolved inward to its current synchronous orbit. The four smaller moons, Styx, Nix, Kerberos, and Hydra, probably formed from residual debris from the same impact event, coalescing into small, irregular bodies that remain in orbital resonances with Charon. The Pluto-Charon system is unique in the solar system for its extreme mutual tidal locking. Pluto not only presents the same face always to Charon, as Earth's moon does toward Earth, but Charon also presents the same face always to Pluto, and both bodies are locked, so their rotation periods match their mutual orbital period of 6.4 days. They form a true binary system, dancing around their mutual center of mass, forever facing each other across the vacuum. This double tidal lock resulted from tidal evolution over billions of years. Tidal forces, differential gravitational pull across each body's diameter, created bulges in each object that, if rotating at different rates than orbital motion, experienced drag that transferred angular momentum. Over time, this process synchronized rotations with orbital motion and caused the system to evolve toward its lowest energy configuration, the mutually locked state observed today. Several other large Kuiper Belt objects possess moons. Haumea has two known moons, Hyakka and Namaka, both likely fragment from the same massive collision that created the Haumea collisional family and set Haumea spinning rapidly. Eris has dysnomia, discovered in 2005, whose orbit allows precise determination of Eris's mass. Makemake has at least one moon, provisionally designated S/2015, 136472, one and informally called two Malawian Quaches, discovered in 2016 using the Hubble Space Telescope. Binary Kuiper Belt objects, systems where two similarly sized objects orbit each other, are surprisingly common. Surveys suggest that roughly 30% of cold classical Kuiper Belt objects exist in binary or multiple systems, a much higher fraction than found among asteroids or hot classical Kuiper Belt objects. This high binary fraction suggests that formation mechanisms in the cold classical belt favored binary production, perhaps through gentle collisions at low velocities that allowed objects to stick together rather than shatter. The orbital characteristics of these binary systems provide valuable data. By observing how long a binary takes to complete one mutual orbit and how far apart the two components are, scientists can apply Kepler's laws to calculate the system's total mass. Combined with estimates of system size from brightness measurements, this yields density estimates that constrain composition and internal structure without requiring spacecraft visits. Haumea's ring system, discovered in 2017 through observations of a stellar occultation, represents a fascinating case of dynamics around a small body. The ring orbits Haumea in its equatorial plane at a distance of approximately 2,000 kilometers from its center, near the 3-to-1 resonance with Haumea's rotation. The ring is narrow and dense, similar in some ways to Saturn's narrow rings, though far less spectacular. The ring's origin remains uncertain. It may consist of debris from an impact, or material from one of Haumea's moons that wandered too close and was torn apart by tidal forces. The existence of rings around such a small body challenges conventional understanding. Rings generally form when material orbits within the Roche limit, the distance inside which tidal forces from the primary body would tear apart a satellite held together only by self-gravity. For Haumea, with its elongated shape and rapid rotation, the Roche limit and orbital dynamics become complex, potentially creating stable or metastable orbits where ring particles can persist. Chariklo, technically not a Kuiper Belt object, but rather a centaur, a former Kuiper Belt object, now orbiting among the giant planets, also possesses rings discovered in 2014. Chariklo's rings are even narrower than Haumea's, with two distinct ringlets separated by a gap. This suggests gravitational shepherding by small, as yet undetected moonlets that confine ring material to narrow bands, similar to how some of Saturn's moons shepherd ring particles. Tidal forces also affect the internal structures of Kuiper Belt objects in close binary systems or with nearby moons. These forces can generate heat through tidal flexing, the continuous deformation of a body as it orbits in an elliptical path or experiences varying gravitational forces. On the icy moons of Jupiter and Saturn, tidal heating drives geological activity, including potential subsurface oceans. Whether similar processes occur in Kuiper Belt binary systems depends on orbital eccentricity and internal structure, but the possibility remains that some systems may experience tidal heating sufficient to maintain liquid water layers beneath their frozen surfaces. Mutual eclipses and occultations in binary systems, when one component passes in front of the other as seen from Earth, provide additional information. The light curves obtained during these events reveal details about shapes, sizes, and surface brightness variations on both components. Long-term monitoring can detect changes in orbital periods that might indicate mass transfer between components or the presence of additional, undetected companions. The gravitational interactions within multiple moon systems create complex dynamics. In a Pluto system, orbital resonances between the small moons and Charon stabilize the system, preventing chaotic orbital evolution that might otherwise eject moons or cause collisions. Similar resonances likely exist in other multiple moon systems, though detailed observations sufficient to detect them require extended monitoring campaigns with powerful telescopes. As you drift past these systems, moons wheeling around their primaries, rings encircling spinning bodies, binary objects dancing around shared centers of mass, you witness gravity's artistry. Even in this remote region, with minuscule masses compared to planets, gravitational forces still sculpt elegant structures and choreograph elaborate dances that continue across the eons. The mathematics that govern these motions, the same equations that describe planetary orbits and galactic structure, operate here in miniature, demonstrating the unity of physical law across all scales and all reaches of the cosmos. Rest in contemplation of these graceful gravitational ballets as you continue through the frozen frontier. Humanity's exploration of the Kuiper Belt began in earnest with the launch of New Horizons on January 19, 2006, from Cape Canaveral, Florida. This spacecraft, approximately the size and mass of a grand piano, embarked on a 9.5-year journey to Pluto, carrying instruments designed to study the dwarf planet and, if possible, additional Kuiper Belt objects during an extended mission. New Horizons achieved the fastest launch speed of any spacecraft leaving Earth, propelled by an Atlas V rocket and assisted by a gravity assist flyby of Jupiter in February 2007. This Jupiter flyby not only shortened the transit time to Pluto by approximately 3 years, but also provided opportunities to test instruments on Jupiter's moons and magnetosphere, ensuring everything functioned correctly before the crucial Pluto encounter. The spacecraft carries 7 scientific instruments. Ralph, a visible and infrared imager/spectrometer, maps surface compositions and temperatures. Alice, an ultraviolet imaging spectrometer, studies atmospheric structure and composition. REX, a radio science experiment, uses radio occultations to probe atmospheric properties. Lori, a long-range reconnaissance imager, provides high-resolution photographs. SWAP and Pepsi measure solar wind and energetic particles, revealing how Pluto's atmosphere interacts with the space environment. Finally, the Student Dust Counter, built and operated by students at the University of Colorado, measures the dust density encountered throughout the spacecraft journey. On July 14, 2015, New Horizons executed its closest approach to Pluto, passing approximately 12,500 kilometers above the dwarf planet's surface at a relative velocity of 13.8 kilometers per second. During the few hours surrounding closest approach, the spacecraft performed a carefully choreographed sequence of observations, gathering data as fast as its instruments could record. The high flyby velocity meant that this was humanity's only chance. No orbit or return visit, just a brief window to capture as much information as possible. The data transmission back to Earth proceeded slowly due to the vast distance and limited power available for the spacecraft's radio transmitter. At approximately 33 astronomical units during the Pluto encounter, radio signals took over 4.5 hours to traverse the distance to Earth, traveling at the speed of light. The data rate was approximately 1,000 bits per second, roughly 100 times slower than a dial-up internet connection from the 1990s. Transmitting the complete data set collected during the Pluto flyby took 16 months, with the last data file arriving in October 2016. Following the Pluto encounter, mission planners searched for additional targets within the spacecraft's reach, given its trajectory and remaining fuel. The discovery of 486958 Arrokoth, originally designated 2014 MU-69, provided an ideal candidate. Located in the cold, classical Kuiper Belt at approximately 44 astronomical units, Arrokoth lay along New Horizons' trajectory with a small course correction required to intercept it. On January 1st, 2019, New Horizons performed the most distant flyby in history, passing within 3,500 kilometers of Arrokoth. The object revealed itself to be a contact binary, two lobes gently joined together, resembling a reddish snowman approximately 30 kilometers long. This gentle merger of two objects, probably occurring at speeds of just a few meters per second, provided direct evidence of how planetesimals formed through gentle accretion rather than violent collisions. Arrokoth's pristine condition, virtually unmodified since its formation 4.6 billion years ago, made it an extraordinary target. Its smooth surface shows minimal cratering, indicating either a very old surface that predates most of the heavy bombardment or a location in the Kuiper Belt where collision rates are extremely low. The object's two lobes likely formed separately and orbited each other before gradually spiraling together and merging, demonstrating a formation process relevant to understanding planetesimal accretion throughout the protoplanetary disk. New Horizons continues outward, currently traveling at approximately 14 kilometers per second relative to the Sun. As of 2025, it lies approximately 60 astronomical units from the Sun, moving through the Kuiper Belt's outer regions. The spacecraft remains functional, with instruments continuing to collect data on the solar wind, interstellar dust, and the interplanetary environment. Mission planners hope to identify additional distant targets for distant flybys, though finding objects close enough to the spacecraft trajectory becomes increasingly challenging as options narrow. The spacecraft power supply, provided by a radioisotope thermoelectric generator fueled by plutonium-238, slowly declines as the plutonium decays, producing less heat over time. Current estimates suggest New Horizons will have sufficient power to operate instruments and communicate with Earth through the 2030s. Eventually, declining power will force difficult choices about which instruments to keep running, followed by increasingly infrequent communications, until finally the spacecraft will fall silent, continuing its outward journey, but no longer able to phone home. Future missions to the Kuiper Belt face significant challenges. The vast distance means travel times of a decade or more, even with our fastest spacecraft. Communication delays of many hours preclude real-time control, requiring spacecraft autonomy. Solar panels become ineffective beyond Jupiter's orbit, necessitating nuclear power sources that are expensive and limited in availability. Nevertheless, the scientific rewards of Kuiper Belt exploration motivate continued mission planning. Concept studies have explored missions to orbit a Kuiper Belt object, to perform multiple flybys of different objects, or to send penetrators or landers to surface study. An orbital mission would allow detailed, long-term monitoring of a target world, observing seasonal changes, searching for ongoing geological activity, and fully mapping surface composition and topography. Such a mission would require substantial propulsion capability to decelerate into orbit after the long journey outward, significantly increasing mission complexity and cost. Sample return from a Kuiper Belt object remains a long-term goal. Bringing pristine Kuiper Belt material to Earth's laboratories would allow analyses impossible with remote sensing alone. Detailed isotopic measurements, organic compound identification, age dating, and study of material properties. However, the round-trip time of decades and the enormous energy requirements make such a mission extremely challenging with current or near-future technology. Ground-based and space-based telescopes continue to discover and characterize Kuiper Belt objects. Large telescopes including the Subaru telescope in Hawaii, the Gemini observatories, and a very large telescope in Chile conduct surveys that discover new objects and perform follow-up spectroscopy to determine compositions. The Hubble Space Telescope has discovered numerous Kuiper Belt objects and monitored known objects to detect moons, rotation states, and surface changes. The James Webb Space Telescope, launched in December 2021, brings unprecedented infrared sensitivity to Kuiper Belt studies. Its large mirror and advanced instruments allow detection of fainter and more distant objects than previously possible, and detailed spectroscopy that can identify a wider range of surface ices and organics. Early observations have already expanded knowledge of trans-Neptunian objects, and ongoing programs will continue revealing the belt's diversity. Continuing exploration, whether by spacecraft or telescope, slowly builds humanity's understanding of this remote region. Each new discovery, each detailed measurement, each high-resolution image adds another piece to the puzzle of how our solar system formed and evolved. The frozen frontier, once completely unknown and unseen, gradually reveals its secrets to patient observation and the brave spacecraft that journey to its distant reaches. As you contemplate these achievements of exploration, take satisfaction in humanity's curiosity and persistence, our drive to understand our cosmic neighborhood, no matter how distant and challenging the journey. The Kuiper Belt exists today as a remnant of our solar system's formation, its composition and structure carrying information about processes that occurred when the sun and planets were young. Understanding the belt's origin requires reconstructing the conditions in the proto-planetary disk 4.6 billion years ago and modeling the complex gravitational interactions that shape the solar system's architecture. Star and planetary system formation begins in giant molecular clouds, vast regions of space filled with gas and dust, cold and dense enough that gravity can overcome internal pressure and cause collapse. When a portion of such a cloud begins to collapse, conservation of angular momentum causes it to flatten into a rotating disk with a forming star at its center. This protoplanetary disk contains the raw materials from which planets will form, mostly hydrogen and helium gas, with roughly 2% heavier elements including rock-forming silicates, metallic iron, and various ices. The temperature in this disk decreases with distance from the forming star. Close to the proto-sun, temperatures are high enough to vaporize even rocky materials. Farther out, temperatures drop below the condensation points of various materials, creating snow lines where different substances transition from vapor to solid. The water-ice-snow line, at approximately 3 to 4 astronomical units in our solar system, mark the boundary beyond which water ice could condense and contribute to planet building. Farther out, carbon monoxide, methane, and other volatile ices could condense, enriching the solid material available for planet formation. In the region that would become the Kuiper Belt, temperatures were cold enough for all major ices to condense. Models suggest temperatures of 30 to 40 Kelvin at 40 to 50 astronomical units, cold enough to freeze carbon monoxide and methane, as well as water, ammonia, and other less volatile ices. The available solid material in this region consisted of a mixture of silicate dust, metallic grains, and various ices in roughly equal proportions by mass, the composition we observe today in Kuiper Belt objects. Planet formation in the protoplanetary disk occurred through a multi-stage process. Initially, microscopic dust grains collided and stuck together through electrostatic forces and molecular adhesion, growing to millimeter and centimeter sizes. These pebbles and small rocks settled toward the disk's midplane, creating a dense layer where concentrations increased and collision rates accelerated. Once objects reached kilometer sizes, called planetesimals, their self-gravity became significant, allowing them to gravitationally attract additional material and grow more rapidly. In the inner solar system, This process continued efficiently, with planetesimals colliding and merging to form ever larger bodies. Moon-sized embryos formed within a few 100,000 years, and these continued growing through giant impacts until they became the terrestrial planets we see today: Mercury, Venus, Earth, and Mars. The process was violent, with countless collisions, massive impacts, and gradual clearing of debris until only a few large planets remained. In the region of the giant planets, a different process occurred. Here, large cores, perhaps 10 to 15 Earth masses, formed rapidly enough to gravitationally capture gas from the surrounding disk before the young sun's radiation and wind dispersed it. Jupiter and Saturn captured enormous gas envelopes, becoming the gas giants. Uranus and Neptune, forming later or in a region where less gas remained, captured smaller envelopes, becoming ice giants with gas envelopes less dominant relative to their icy rocky cores. The Kuiper Belt region, however, experienced different conditions. The low density of material at this great distance meant planetesimals formed, but the growth rate was slow. Collisions occurred infrequently due to the large orbital spacings. Before objects could grow large enough to gravitationally dominate and clear their orbits, the formation process was interrupted by the gravitational influence of the newly formed giant planets, particularly Neptune. Current models suggest Neptune formed much closer to the Sun, perhaps at 15 to 20 astronomical units, and migrated outward over tens of millions of years. This migration was driven by gravitational interactions with the remaining planetesimal disk. As Neptune scattered planetesimals inward, the reaction pushed Neptune outward through conservation of angular momentum. This outward migration had profound effects on the outer solar system. As Neptune migrated outward, it swept through the region that would become the Kuiper Belt, scattering most material it encountered. Some planetesimals were ejected from the solar system entirely. Others were scattered inward, potentially contributing to the late heavy bombardment of the inner planets. A small fraction of objects became trapped in orbital resonances with Neptune. The Plutinos, Titinos, and other resonant populations swept outward as Neptune's resonances moved with it. The objects beyond Neptune's final orbit at 30 astronomical units, particularly those in the cold classical belt, largely escaped this scattering. Their stable, low-inclination, circular orbits reflect primordial conditions. They formed at roughly their current locations and have remained there, minimally disturbed, for 4.6 billion years. These objects represent the most pristine samples of the outer protoplanetary disk available for study. The scattered disk population formed from objects that experienced strong gravitational encounters with Neptune, but were not ejected from the solar system. Each close approach changed orbital energy and angular momentum, gradually pumping up eccentricity and inclination, flinging objects onto the highly elliptical orbits observed today. This process continues at a reduced rate even now, slowly depleting the scattered disk as objects either escape the solar system or have their perihelia lowered until they enter the planetary region and potentially become short-period comets. The Kuiper Belt's relatively low mass, perhaps 10 to 100 times less than would be expected from simple extrapolation of the protoplanetary disk surface density, suggests that most material was removed from this region. Neptune's migration likely scattered away 99% or more of the original mass. The objects remaining today are survivors, the lucky ones that avoided close encounters or were protected by resonances. Isotopic evidence from comets supports formation in the outer solar system. The deuterium to hydrogen ratio in water varies with formation temperature, with colder formation environments producing higher ratios. Kuiper Belt comets show deuterium to hydrogen ratios consistent with formation at the temperatures expected in the outer protoplanetary disk, confirming their origin beyond the ice giant planets. The presence of crystalline water ice on some Kuiper Belt objects initially puzzled scientists, as formation at their current locations should produce amorphous ice. Several explanations have been proposed. Perhaps objects formed closer to the sun where temperatures were warmer and were later scattered outward by planetary migration. Perhaps radioactive heating or impact heating crystallized initially amorphous ice. Or perhaps crystalline ice forms directly under certain conditions in protoplanetary disks. The answer may differ for different objects, adding to the belt's diversity. The formation of binary and multiple systems in the Kuiper Belt also provides clues about formation conditions. The high binary fraction among cold classical objects suggests formation through gravitational collapse of local overdensities in the disk, regions where material concentrated and collapsed directly into multiple bound objects. This formation mechanism bypasses gradual growth through collisions and may explain how kilometer-sized planetesimals could form rapidly despite the challenges of collisional growth in low-density environments. As you contemplate these formation processes, you witness the Kuiper Belt as both an end product and a window into the past. These frozen worlds are remainders, leftovers from the solar system's construction, preserving in their icy bodies the chemicals and conditions present at the solar system's dawn. They are simultaneously ancient archives and ongoing experiments in slow chemistry and physics, continuing to evolve across deep time while retaining memory of their origins. Understanding their story means understanding our own origins, for we too are products of the protoplanetary disk, built from materials that condensed and accreted in warmer regions of the same disk that created the Kuiper Belt's frozen denizens. As you drift toward the outer boundary of the Kuiper Belt, approximately 50 astronomical units from the Sun, the population of objects begins to thin. The classical belt's sharp outer edge appears before you. Beyond it, the density drops precipitously. This boundary, sculpted by Neptune's gravitational influence during its migration, marks the practical outer limit of the Kuiper Belt proper, though scattered disk objects on highly elliptical orbits extend much farther. Beyond this edge lies the scattered disk's sparse population, objects on eccentric orbits carrying them to tremendous distances before plunging back toward the inner solar system. Still farther out, at distances of 1,000 astronomical units and beyond, begins the Oort cloud, a vast spherical shell of comets surrounding the solar system. Though too distant for New Horizons or any current spacecraft to reach in a human lifetime. Here at the edge of the belt, the Sun appears merely as the brightest star in the sky, providing negligible warmth but still sufficient light to navigate. The temperature asymptotes toward the cosmic microwave background temperature of 2.7 Kelvin, the residual heat from the Big Bang itself, which permeates all of space and represents the coldest possible temperature that can be reached through passive cooling. Looking back toward the inner solar system, you see the Sun's light reflected from countless ice worlds, each a tiny glint in the darkness. The 4 giant planets would be visible as bright points, easily outshining the stars, their reflected sunlight making them prominent even at these distances. The inner planets, including Earth, would be invisible, lost in the Sun's glare, too small and too close to our star to be distinguished from this remote vantage point. The Kuiper Belt has revealed itself to you as a realm of surprising diversity within apparent monotony. All is ice and rock, cold and dark. Yet within these constraints exists remarkable variety, compositions varying from pure water ice to methane, nitrogen, and complex organics, orbits ranging from nearly circular to wildly eccentric, surfaces from bright and fresh to dark and ancient, objects from pebbles to dwarf planets, isolated wanderers and binary companions, cratered ancient terrains and young, refreshed plains. This frozen frontier challenges our terrestrial intuitions about worlds. Here there are no atmospheres in the conventional sense, only tenuous exospheres that freeze out at the slightest cooling. There is no weather as we know it, though nitrogen snow may fall on Pluto during certain portions of its orbit. There is no liquid water shaping landscapes, though liquid water may hide beneath ice shells on the largest objects. There is no life, at least none that we have detected or could imagine surviving in such cold, dark isolation, though the organic chemistry occurring here over billions of years contributes to the inventory of molecules from which life eventually emerged on Earth. Yet the Kuiper Belt pulses with its own character, the slow drift of objects along ancient orbits, the rare violence of impacts, the patient chemistry driven by radiation, the gravitational dances of moons and binary systems, the gradual evolution toward lower energy states through tidal interactions. This is not a dead region, but an active one, merely operating on timescales that dwarf human experience and at temperatures that challenge our ability to relate to the physics at work. Scientific understanding of the Kuiper Belt has exploded over the past 3 decades. What was once merely a theoretical prediction, an expected population of objects needed to explain short-period comets, has become a detailed, observed reality with thousands of catalog members and more being discovered regularly. New Horizons transform 2 objects from points of light into detailed worlds with landscapes and geologies. Ongoing telescopic observations continue revealing the belt's structure and composition with increasing precision. Yet much remains unknown. The total population of objects, especially smaller bodies below current detection limits, remains uncertain. The detailed compositions of most objects await future spectroscopic observations. The interior structures, whether differentiated or homogeneous, whether harboring liquid layers or uniformly frozen, remain largely theoretical. The formation mechanisms of binary systems, the origin of objects on extremely distant orbits like Sedna, the possible existence of additional large planets in the outer solar system, all these questions await answers. Future exploration will gradually address these mysteries. More powerful telescopes will discover fainter objects and characterize compositions more precisely. New spacecraft missions, perhaps decades in the future, will return to examine additional Kuiper Belt objects up close. Computer simulations will grow more sophisticated, incorporating additional physics and running on more powerful hardware, refining models of formation and evolution. Slowly, patiently, the frozen frontier will yield its secrets. For now, as you drift here at the edge of the Kuiper Belt, absorb the profound peace of this realm. The vast distances ensure solitude, each object separated from its neighbors by millions or billions of kilometers of empty space. The cold ensures stillness, no winds, no waves, no weather to disturb the ancient surfaces. The darkness ensures quiet contemplation. With the sun reduced to merely the brightest star, you can perceive the universe beyond. The stars of our galaxy stretched across the sky, the faint band of the Milky Way visible in full glory, unmarred by light pollution or atmospheric scattering.